In this session, we will continue continuous distributions with gamma and exponential distributions. They're usually used for lifetime variables where the variable cannot take negative values, like lifetime of something, right? It cannot take a negative value. And those distributions have two parameters. It is which one, the first one is, this one is your shape parameter. Shape parameter, it is denoted with K or alpha in our textbook, okay? And also its scale parameter, where is the average is located here, and this is called the scale parameter, and it is denoted with theta or beta in our textbook. Those are used in our textbook. And the thing is, let me try to use this space here. So its probability density function is something like this. Y is y minus 1 times alpha y over beta, which is over beta over alpha. It's the ceiling function of the alpha, where your y is greater than or equal to 0 and alpha and beta are greater than 0. This is called the gamma density function here. The density function here is 0 to y to the power minus 1 e minus 1 dy. This is required for calculating those areas under the curve. That's the idea, okay? So we're not going into details of the proofs here, but that is roughly what we have for the functions of gamma here, gamma distribution here. If you take a look at some different curves, I have taken this from Wikipedia. I cannot remember now. It's the graph is a bit different from what has been used in our textbook. As you see that if your K drops here, your shape parameter drops here, it makes it more sharp, as you see. And if it is so it is just becoming a bit sharp here with the curve, and if you increase it, it becomes a bit flatter. And again, if your theta drops here, it raises here, as you see. This one has the highest value here, gathered here, and if you have it, for example, increased, it will be pressed down. That's the idea about how the shape looks. But of course, it is coming from those formula, but we're not going into detail. The expected value or the mean of this gamma distribution is alpha times beta, and the variance of y is, which is your standard deviation square, which is alpha times beta square here. Now, this is all about gamma distribution, and when your shape parameter is not an integer value here, as you see, all of your shape parameters are integers values here. If it is not an integer value, a computerized approximation approach is used for calculating the gamma density function, for calculating the area under that curve. Manual calculation would not be possible. That's the idea. And when your shape parameter value is strictly equal to 1, it is now called the exponential distribution, which is a special case of your gamma distribution. Now let's take a look at it. The thing is, in this particular condition where your k is 1, it has another name, which is called exponential distribution. So in fact it's a gamma distribution, but if k is 1, it is called exponential distribution. How can we use this? Like it's like the delta t time time passed between customer requests, like it can correspond to your beta parameter here, or average number of customers that will be there in that time. It can also be, I mean, it's pretty similar to Poisson distribution function, but the continuous version of it. And its probability density function is, not surprisingly, we will just drop the alphas here. It is 1 over beta b. Since your k is 1, we will drop the alpha and k here. 1 over beta is 1 e to the power minus y over beta. This is your probability density function where your beta is greater than 1 and your y is greater than or equal to 0 here. And what would be the expected value or the average of your function here, exponential function? It's beta. If you remember, it was alpha times beta, but since your alpha is 1, it is beta. And in gamma distribution, it was, if you remember, alpha times beta square, right, in gamma distribution. But here, if your alpha is 1, your variance will be beta square. Now, these are all formulations which can be a bit rather boring, but if we try to, have an example, maybe we can understand it better. So, it is, but what we should keep in mind is it is closely related to Poisson distribution. And you can call it as the continuous version of Poisson. Okay, so let's try to solve an example from our textbook. Now, a quality control question. Quality control question. A lifespan of a microcomputer shows, okay, lifespan of a microcomputer shows y, a parameter beta as 100 hours, exponential distribution. So what would be your average and what would be your variance? This is what is being asked to us, and this is the first part of the question that we need to address. So if you remember, our EY was directly beta, right? No, it was directly beta. So this is, if your distribution is showing exponential distribution with beta equals 1000, So your average will be 1000 as well, 1000 hours, and your variance would be square. It's square of it. It is 10 to the power 6, as of course it doesn't have a unit. So that would be your variance. Now there can be several questions that can be asked here. Let's try to answer them. The first one is what is the probability that your y is greater than 2000? So what do we have here? In fact, a distribution like this, and it is asking us what is the probability of this one being more than this area under this curve. This is what we're trying to find here. So it should be something small, and because it's since you're let's say 1000 is here, I'm just trying to put this. It should be something small. What we're expecting should be small. So the probability of y is greater than 200 can be shown with 1 minus probability of the probability of y less than 2000, right? So what I do here is I'm trying to calculate the area under this curve, then subtract it from 1. This is how I can approach this problem. So for this purpose, we need to calculate 1 minus this partial integral from 0 to 2000, 1 over 10 e to the power minus 1 over 1000 dy. I mean, how do we write this? Let me just try to remind you, if you would like, if you remember it from calculus. I'm not sure you had this, just for you to remember. Okay, no need to prove anything later, but that's what we're doing here, in fact, to make that calculation. 3x squared dx would be written as this one, right? So this one is coming right here, so that's the and if you have it for ex dx, you have it as ex, again the same, c. And if you have partial integral here from a to b, and suppose that fx dx would be b minus f a. So but the thing is, for example, if you have it e x dx would be minus 1 over 3 e plus c. So the thing is, when you put them here in their positions here, like this one, if we come back to this one, for this purpose, we will write for this one, just try to write here. What is your y? It is 2000, right? This one is 2000, that would be right here. So it should be minus 1 over 1000, over 1 over 1000 e to the power minus 2 minus, okay, this is since this one is, as you see, it is 2000 over 1000, right? That's why we have 2 here. Okay, we calculated for this one minus, and this one f0 should be, okay, minus the 1000 over 1000 e to the power 0 here for 0, and the result will be minus e to the power minus 2 plus 1 here. Since it is minus and minus here, it would make plus, and the result would be minus 1 minus e square here. That's what you have here, and that's what you need to put right here instead of this one. If you're familiar with this type of questions, you can directly go ahead and make the calculation. It doesn't matter. I'm not expecting you to prove anything here, but just to give you an idea about what we're doing here. Okay, this is the thing that maybe you can remember this. 1 minus 1 plus e to the power minus 2, and what you have here will be 0.534, and roughly that should be what? This is the probability that you're looking for. Probability of y is greater than 2000. Should be something like this, which is 3-4%. Okay, it's like 13% or something like this. That would be the answer to question part B of the question. Now, if we continue with the other part of the question, let's try to solve another one where you say, suppose that this is the C part. Your lifetime, what is the probability of your lifetime being less than 1500? So in this sense, no need to prove here, but let's just try to make the calculation directly here. 1 minus e to the power 1 will directly give you the area under that curve, right? So now what I'm trying to calculate is something like this. Okay, so here you have your 1000, here you have your 1500, and you're trying to calculate the area directly under this curve. See, it would be something large. Maybe more than 50% or something, so you can make an estimation here. So that would be 1 minus e to the power minus 1.5, and of course you will have a calculator, and you can calculate it like this, and the result will be 0.778. So it is again 77%, approximately 77% would be your probability of y being less than 100 hours. Okay, I think that makes sense. It is logical. You can keep it, can use this e to the power minus lambda values directly here from your readily available table in your textbook as well. If you don't want to use your calculator, you can rely on that table as well, but you can use your calculator too. It doesn't matter anyway. So, and have you noticed something? We have already calculated lots, and now we can make like an extra step here. We can take an extra step here just to give you an idea about what is going on. So here, this was your 1000, and this was your 50, and this was your 2000. We have already calculated this probability, right, in part B, and we have already calculated this probability in part C, right? B in part B and C. Now let's devise another question together, which is called, let's calculate the probability under this one, which is your D, can be calculated, can be defined and calculated. What is the probability of your Y being between 1,500 hours of operational lifetime and operational lifetime and is what? I think it's pretty obvious, right? We need to subtract this one and this one from what? 1, and we will get that result 2. So what is it? It is probability of 1 minus probability of Y less than 100 minus probability of Y greater than 1000 hours. That's it. So we have already calculated these ones, right? So let's say that it's 0.13. This one is use the blue color, 0.13 and 534. And what was this one? It was 0.7768. Great. So when you subtract it from 1, since you have a calculator, you will have a value like this, 0.08779, and it is roughly 8.77% probability, and that would be the probability for between 1,500 operation hours and 2,000 operation hours here. Okay, that would be your let's say this is your D part, and that would be your last example about exponential or gamma distributions at all. Okay, this is all about the exponential distribution. You can use this for quality control purposes, insurance claim calculations, for predicting rainfalls, probabilities, etc. in that type of domains particularly. Okay, thank you for listening.